we go with today's ology video, second of 3 videos today. As of St. George's one before and the news one after this at some point. Today's ology is meteorology, kind of following on from cosmology and astrology last week, last Thursday and Friday, so here we go. Meteorology is a branch of science that is concerned with the process of phenomena of the atmosphere, especially as a means of forecasting the weather, like the climate and weather of a region. Now, not every regional country has the same thing. So yeah, it comes from the early 17th century. Greek word meteorologia, which comes from the Greek word of meteoron, which means of the atmosphere. And it's meteorology is the study of the atmosphere, atmospheric phenomena and atmospheric effects on our weather. The atmosphere is a gaseous layer of the physical environment that surrounds the planet, beyond above the crust kind of thing, and above the oceans. Earth, as our atmosphere, is roughly about 100 to 125 kilometers or 60 to 75 miles thick. And gravity keeps the atmosphere from expanding much farther. Meteorology is a sub-discipline of the atmospheric sciences, a term that studies the atmosphere. Now, a sub-discipline being a specialised field of study within the broader subject or discipline. Now, it's climatology and aeronomy are also sub-disciplines of atmospheric sciences. Climatology focuses on how the atmospheric changes define and alter the world's climates. Aeronomy is the study of the upper parts of the atmosphere where unique chemicals and physical processes occur, whereas meteorology focuses on the lower parts of the atmosphere, primarily the troposphere, where most of the weather takes place. Yes, and meteorologists use scientific principles to observe, explain, and forecast our weather, and as they often focus on atmospheric research or operational weather forecasting. Now, research meteorologists cover several sub-disciplines of meteorology, to include climate modelling, remote sensing, air quality, atmospheric physics, and climate change. And they also research the relationship between the atmosphere and Earth's climates, oceans, and biological life. They kind of interweave and yeah. So yeah. Forecasters then use that research along with atmospheric data and scientifically access the current state of the atmosphere, and make predictions of its future state. Now, the atmospheric conditions both at the Earth's surface and above are measured from a variety of sources: weather stations, ships, buoys, aircraft, radar, weather balloons, and satellites. It's all very high tech. And this data is transmitted to centres throughout the world to produce computer analysis of global weather. Now, the analyses are passed on to national and regional weather centres, which feed the data into computers that model the future state of the atmosphere. And this transfer of information demonstrates how weather and the study of it takes place in multiple interconnected ways. Yes, weather occurs at different scales in like space and time, and there's like 4 micro meteorological scales, which are microscale, mesoscale, synoptic scale, and global scale. As meteorologists often focus on a specific scale in their work, as it might be a little too much for them to kind of do all of them. Microscale meteorology is like focus on the phenomena that range from a few centimeters to a few kilometers, and have a short lifespan, which can be considered like less than a day. These phenomena affect very small geographic areas and the temperatures and terrains of those areas, as they often study the processes that occur between the soil, vegetation and the surface water near ground level, and they only measure the transfer of heat, gas and liquid between those surfaces. Micrometeorology is often the study of the chemistry. Like tracking air pollutants is an example of microscale meteorology. Like Meteorology Mexico is a collaboration between meteorologists in the United States and Mexico. That's where it's scaring me as the screen just goes green for a second. The program studies the chemical and physical transformation of gases and aerosols in the population surrounding Mexico City. Meteorology Mexico often uses like observations from ground stations, aircraft and satellites to track said pollutants and all. Mesoscale meteorology is range in size from a few kilometers to about 1,000 kilometers, or roughly 620 miles. And the important phenomena are mesoscale convective complexes (MCC) and mesoscale convective systems (MCS). Both are caused by convections are important meteorological principles. Convections is a process of circulation. As warmer, less dense fluids rise and the colder, denser fluid sinks. The fluids that most meteorologists study is air. Like any substance that flows is considered a fluid, whether it be like a gas, liquid or solid or whatever. Convection results in the transfer of energy, heat and moisture is a basic building block of weather. In both MCC and MCS, a large area of air and moisture is warm during the middle of the day, when the sun's angle is at its highest. As the warm air rises into the colder atmosphere, it condenses into clouds, turning like the vapour into precipitation. The MCC is a single system of clouds that can reach into this. It can reach to the size of the state of Ohio and produce heavy rainfall and flooding, while an MCS is a small cluster of thunderstorms that can last for several hours. Both react to a unique transfer of energy, heat and moisture caused by convection. The deep convective clouds in chemistry, DC3. Field Campaign is a program that will study storms and thunderclouds in Colorado, Alabama and Oklahoma. This project will consider how convection influences the formation of storms, including the development of lightning. It also studies the impact on aircraft and flight patterns. The DC3 program uses the data gathered from research aircraft able to fly over the tops of the storms. The synoptic scale phenomena can cover an area of several hundred, even thousands of kilometers. High and low pressure systems can, on local weather forecasts, are synoptic in scale. Pressure, much like convection, is an important meteorological principle that is at the root of large-scale weather systems as diverse as hurricanes and bitter cold outbreaks. They're a bit like the beast from the east that we've had over here recently. Like low pressure systems occur when atmospheric pressure at the surface of Earth is less than its surrounding environment. Wind and moisture from areas with high pressure seek low pressure systems. This movement in conjunction with the Coriolis force and friction and causes the system to rotate counterclockwise in the northern hemisphere and clockwise in the southern hemisphere, creating a cyclone. Cyclones have a tendency for upward vertical motion. This allows moist air from the surrounding air to rise, expand and condense into water vapour, forming clouds, and this movement of moisture and air causes the majority of weather events. And whereas hurricanes are a result of low pressure systems, cyclones developing over tropical waters in the western hemisphere. The system sucks up massive amounts of warm moisture from the sea, causing convection to take place, which in turn causes wind speed to increase and pressure to fall. When these winds reach over 119 kilometers an hour, or 74 miles per hour, the cyclone is then classified as a hurricane. And as hurricanes can be one of those devastating natural disasters in the western hemisphere, the natural hurricane centre in Miami, Florida, regularly issues forecasts and reports on all tropical weather systems during hurricane season. Hurricane specialists issue forecasts and warnings for every tropical storm in the western tropical Atlantic and eastern tropical Pacific. Businesses and government officials from the United States, the Caribbean, Central America and South America rely on forecasts from the National Hurricane Center. Now, high pressure systems occur when the atmospheric pressure at the surface of the Earth is greater than its surrounding environment. This pressure has a tendency for downward vertical motion, allowing for dry air and clear skies. Extremely cold temperatures are a result of high pressure systems that are developed over the Arctic and more over the northern hemisphere. Arctic air is very cold because it can be cold because it develops over ice and snow covering the ground. This cold air can be dense, pushes the Earth against the Earth's surface with extreme pressure, preventing any moisture or heat staying within the system. So again, as a result, many meteorologists have identified many semi-permanent areas of high pressure. The Azores are high, for instance, is a relatively stable region of high pressure around the Azores. The Azores being an archipelago in the mid-Atlantic Ocean. The Azores are high is responsible for arid temperatures in the Mediterranean basin, as well as summer heat waves in the Western Europe. And then there's global scale meteorology, where they look at weather patterns related to the transport of heat and wind and moisture from the tropics to the poles. As it's an important pattern in global atmospheric circulation. large-scale movements of air that helps distribute thermal energy or heat across the surface of the Earth. No, global atmospheric circulation is like kind of like a constant movement of wind across the globe, as when the winds develop as an air mass move from areas of high pressure to low pressure. Global atmospheric circulation is largely driven by Hadley cells. Hadley cells are tropical and equatorial convection patterns. Convection, as the convection drives warm air high into the atmosphere, while cool dense air is pushed, which is low and in a constant loop. Each loop is a Hadley cell. Those Hadley cells determine the flow of trade winds, which meteorologists forecast. Businesses, especially those exporting products across the ocean, pay close attention to the strength of the trade winds, because they help ships travel faster. Waterlines westerlies are winds that blow from the west of the mid-latitudes. Around the equator, closer to the equator, trade winds blow from northeast, north of the equator, and southeast, south of the equator. Meteorologists study the long-term climate patterns that disrupt global atmospheric circulation. Meteorologists discover the pattern of El Nino, for instance. El Nino involves the ocean's currents and trade winds across the Pacific Ocean. As El Nino occurs roughly every 5 years, disrupting global atmospheric circulation and affecting local weather and economics, from Australia to Peru. Now, El Nino was linked to changes in air pressure in the Pacific Ocean, known as the Southern Oscillation. Where air pressure drops over the eastern Pacific near the coast of the Americas, where air pressure rises in the western Pacific near Australia and Indonesia. When trade winds weaken, the eastern Pacific nations experience extreme rainfall, and warm ocean currents reduce fish stocks, which depend on the nutrient-rich upwelling of cold water to survive, while western Pacific nations experience droughts, which can be devastating to agricultural production. Understanding the meteorological process of El Nino helps farmers, fishers, and coastal residents prepare for climate patterns. The development of meteorology is deeply connected to developments in science and maths and technology. When our old friend, the Greek philosopher Aristotle, wrote the first major study of the atmosphere around 340 BCE. Many of Aristotle's ideas were, in fact, incorrect, but because he did not believe it was necessary, that it was necessary to make scientific observations. Now, a growing belief in scientific method profoundly changed the study of meteorology in 17th and 18th centuries, there's Evangelista Torricelli, an Italian physicist, observed that changes in air pressure were connected to changes in weather. In 1964, Torricelli invented a barometer to accurately measure the pressure of the air. The barometer is still a key instrument in understanding on forecasting weather systems today. And in 1714, Daniel Fahrenheit, you can probably see where this is going already, a German physicist developed the mercury thermometer, as these instruments made it possible to accurately measure two important atmospheric variables. And there's no way to quickly transfer weather data until the invention of telegraphy by American inventor Samuel Morse in the mid-1800s. Using this new technology, meteorological officers were able to share information and produce the first modern weather maps. These maps combined and displayed more complex sets of information, such as isobars, the lines of equal pressure, and isotherms, the lines of equal temperature. Just add another one of those green thingies. With these large-scale weather maps, meteorologists could examine a broader geographic picture of weather and make more accurate forecasts. In the 1920s, a group of Norwegian meteorologists developed the concept of air masses and transfer, which are now the building blocks of modern weather forecasting. Using the basic laws of physics, these meteorologists discovered huge cold and warm air masses, and even meeting patterns that are the root of many weather systems. There's and even wars can help as military operations during World War I and subsequently World War II brought advances to meteorology. The success of these operations were highly dependent on weather over vast regions of the globe. The military invested heavily in training, research, and new technologies to improve their understanding of weather. The most important of these the most important of the new technology was radar, which was developed to detect the presence, direction, and speed of aircraft and ships. And since the end of World War II, radar has been used to improve to detect the presence, direction, and speed of precipitation and wind speeds. Now, the technological developments of the 50s and 60s made it easier and faster for meteorologists to observe and predict weather systems on a massive scale. And during 1950s, computed in the first models of the atmospheric conditions by running ahead hundreds of data points through complex equations. These models were able to predict large-scale weather, such as a series of high and low pressure systems that circle our planet. TIROS, TIROS, the first meteorological satellite, provided the first accurate weather forecast from space in 1962. The success of that satellite prompted the creation of more sophisticated satellites, as their ability to collect and transmit data with extreme accuracy and speed made them indispensable to meteorologists today as advanced satellites and their computers. And the computers that process the data is a primary tool used in meteorology today. And meteorology today has like a variety of tools to help them examine, describe, model and predict weather forecast systems. These technologies are being applied to different meteorological scales, improving forecasts and accuracy efficiency. My radar is still an important remote sensing technology used in forecasting. A radar dish is an active sensor that sends out radio waves that bounce off particles in the atmosphere and return to the dish. The computer processes these pulses and determines the horizontal dimension of clouds and precipitation and the speed and direction in which these clouds are moving. As a new technology known as dual polarization radar transmits both horizontal and vertical wave pulses. With this additional pulse, dual polarization radar is better able to estimate precipitation. It is also can be better to differentiate types of precipitation like rain, snow, sleet or hail. As dual polarization radar will greatly improve flash flood and winter weather forecasts. As tornado research is another important component in meteorology. Starting in 2009, the National Oceanic and Atmospheric Administration, NOAA, and the National Science Foundation conducted the largest tornado research project in history, known as Vortex 2. The Vortex 2 team consisted of around 200 people and more than 80 weather instruments as they travelled more than 16,000 kilometres, about 10,000 miles, from the Great Plains of the United States to collect data on how and when and why tornadoes form, specifically. As the team made history by collecting extremely detailed data for during and after a specific tornado. That's why I got something in my eye. The tornado is most intensely examined in history and will provide insights to the dynamics of a tornado. The satellites can be extremely important to our understanding of the scale of weather phenomena. The National Aeronautics and Space Administration, also known as NASA, and NOAA operate three geostationary, operational and environmental satellites (GOES) that provide weather observations for more than 50% of Earth's surface. And GOES 15 was launched in 2010 and it includes a solar X-ray imager that monitors the sun's X-rays for the early detection of solar phenomena such as solar flares. Solar flares can affect military and commercial satellites communications around the globe. A highly accurate imager produces visible and infrared images of the surface, oceans and cloud cover and severe storm developments, while the infrared imagery detects the movement and transfer of heat, improving our understanding of global energy balance and processes such as global warming, convection and severe weather. So yeah, this is me, a brief introduction on meteorology. Today the information I found for a lot of the information I found today was on the National Geographic website. So yeah, I'll see you all very soon. So yeah, bye for now.